Welcome, everyone. This is the last lecture in this introductory course of the program to data science and artificial intelligence. I hope you can hear me.
Yes, perfect.
Okay, very good. So I'm going to share a link to the slides in the chat now. And we will try to cover a very important part of data science that has been just very briefly touched upon so far, namely evaluating the models that we use. This is mostly applied to machine learning, but you can evaluate whatever models you are using. So then let's start for today. I would like to welcome those who might not have been here earlier, but I think with most of you we have already met. My name is Krzysztof Korac, and as I mentioned, we're going to discuss model evaluation and model selection as well afterwards. So the primary question when we have a model in an artificial intelligence system is that how well it's going to work on the data that we are going to be using it for. And in more technical terms, this could be put as how predictive is our model that the learning algorithm created based on a data set, which we provided with for the training session. So some of the the metrics, the evaluation metrics, have been already shortly touched upon, and these include error rate, for example, which you have seen for different models. And this is computed from the success rate by subtracting it from 1. And basically, these are fairly simple to use. One measures how much, what is the ratio of predicting a sample correctly, and the other one is what is the ratio of predicting it incorrectly. So for some other models, like probabilistic models, there can be different error measures, which we will talk about. And also for numerical predictions, like regression models, there are, again, different error measures. The most famous or most widely used one is the squared error or mean squared error, which we will also mention today. But before we start detailing going into the details, I would like to quickly discuss actually a couple of the most pressing things, which we mustn't forget about before we get into mathematical formulae. The first one is that if we want to measure either success rate or error rate, then of course the most trivial thing we can do is to do it on the data set that we use to create a model. And this is what we refer to as the training data. However, if we measure the performance of the model on the very same data set, then it's going to be overly optimistic because it was exactly what we trained it on. If you try to test your knowledge, the good way to go is to use samples that were not included during the training. So if you think about an exam situation, an exam can give you a good assessment about your knowledge if the questions at the exam are different than the ones that you practiced during your learning, because that means you can apply your knowledge to new inputs or to new samples. So this is one of the important things to mention. Another one is the phenomenon of overfitting, which some of you might be familiar with, and we already sort of mentioned both yesterday and the day before that. And this basically just corresponds to how complex a model is. So this should also be taken into account when we do evaluation. And actually, the methodology in evaluation will be able to predict somehow how much overfitting happens. So the most important tool when starting to talking about evaluation is the concept of the test set. This should be a data set which comes in the same form as in the training set. And of course, if we are talking about supervised learning, then this also has to have labels similarly to the original set. If you have a single data set, you might have the chance to decide which part is going to be the part used for training, and which is going to be the part that is used for testing. And then these are going to be the ones we can refer to as the training set and the test set. But both of them, we think about both of them as being representative samples of the underlying problem. However, there might also be some differences between the two, especially in the distribution of the samples. And if you are in a situation where you cannot choose which part, the training part and the test part yourself, you're given just training samples, and then you're going to be given test samples later, then there's a good probability, or at least a good chance, that the distribution of the test set is going to be different from the training set. This difference can be both in terms of the input attributes. So it's coming from, there might be more samples from one part of the input space in the test set than in the training set. And it might also be in terms of the labels. So some classes might have more samples than the others. One very important reminder when you are doing evaluation and using a test set is not to use the test set for evaluation if you want to get an objective measure of your performance, or the performance of your model. And if the test set gets used, then we talk about data leakage, and it will basically deteriorate the estimations that you have from the evaluations about the model performance. And this can actually occur in multiple ways as when you start doing more complicated things in the machine learning flow. We will talk about model selection, for example, today, or tuning of the models, or even just deciding how long you are training your models. If you happen to use your test set for any of these steps in your process in any way, then data leakage already occurs. So you better lock your test set. If you have access to your test set when you start training, you better try to lock it away somehow in a safe, for example. I mean, I'm talking figuratively, of course, but actually data leakage occurs very frequently, even among data scientists who do have a long experience, sometimes only because of not paying enough attention. So what we expect from the test set is to be representative of the underlying problem, as we mentioned it earlier, but I also mentioned it that there might be differences between the two test sets, and these can only also occur because the test set was sampled in a different time than the training set, for example. So in a business scenario, when businesses try to make decisions during the COVID pandemic, using data that was gathered previously, then the performance of those models trained earlier actually fell quite significantly because of the very different nature of the samples coming in this new era. All right. So I'm going to start discussing the metrics in detail that are typically used after these initial thoughts. But before we get into those, I would like to ask if there are any questions so far. Okay, I don't see any questions in the chat, and thanks for those who have reshared the link to the slides for those who didn't arrive on time. So I'm just going to proceed now. So the most basic thing where we can define these metrics are interpreted for binary classification. And in these cases, we have just two classes, one of which we typically refer to as a positive class, and the other one, the negative class. And you could think of the positive class when the answer to the classification problem is yes, or you should frame the question in a way so that you could answer yes. And the negative class is where the answer is no. And because you have in supervised learning, you have a label for each of your samples, and you're going to predict a label. This basically creates 2 times 2 possibilities for the outcome of the prediction. If the actual class predicted by the label is positive and the model predicts a positive label, then we are talking about a true positive case. The other true case is when you get it correctly for the negative label. It's called a true negative scenario. And these correspond to the main diagonal of this so-called confusion matrix. And the reason it is called confusion matrix is for the case when the prediction is actually incorrect. And in this binary case, there are two such scenarios, one of which is called the false negative, and the other one is called the false positive. We also refer to these as type 1 error for the false positive cases and type 2 error for the false negative cases. Why do we call this case a false positive, where the actual class is negative, negative and the prediction is positive? So when you are a predictor, you don't know, or you shouldn't know, what the ground truth label, the actual class is. You are just picking one. Your prediction, in this case, as indicated by the column, is that you will predict the label to be positive. However, when you do the evaluation and you learn about the ground truth, then you realize that this positive prediction was not correct. So it's a false prediction, and that gives the name false positive prediction to this quarter of the confusion matrix. And similarly, if the predictor predicts a negative label but doesn't get it correctly, because the actual truth that this sample belongs to the positive class, then this is going to become a false negative prediction, or a type 2 error. Now, based on these basic definitions, we can define the success rate and the error rate we talked about so far using these values. The success rate is basically the ratio of all true positive plus true negative cases to all the predictions made. So the sum of all 4 categories from the confusion matrix. And the error rate is just 1 minus the success rate, or you can just say that all the falsely predicted cases, the ratio of all the falsely predicted cases out of all the predictions. Now, more advanced measures include the ones that you can see lower on the slide. So one possible view that we can take is to go for evaluating our predictions with the focus on the true positive predictions. And there are 2 important things for the true positive predictions to happen. What is the ratio of the true positive predictions out of all of the positive cases? So how many of the positive cases could the model predict correctly to be positive? This is what we call precision. And the other aspect where we compare the true positive cases to the ones to the samples that were predicted to be positive. This corresponds to the vertical ellipses here on the right-hand side confusion matrix. In this case, we are comparing true positive to the positively predicted cases, and then we are sorry, I was wrong. This corresponds to the horizontal ellipses. So then we are going to compare it to the case where the true positive cases are divided by all the positive cases. So here in the formula of the recall value, which is called a recall, you could actually just write simply P as letter P for all the positive cases, and for the precision are the ones where you compare it to the true positives plus false positives. So all the samples that were predicted to be positive. Sorry for mixing and doing a bit of confusion here earlier. And there's another aspect which is commonly used or were introduced basically in medical testing, where we use two different analyses. Actually, one of them is the same when we compare the true positives to the ratio of all positive values. And this is, in this scenario, this is called sensitivity. And the corresponding other evaluation metric here is called specificity, which basically predicts the ratio of the correctly negative predictions to all the negative samples. So we have to add in the denominator, we have to add the false positive and the true negatives to get the total number of negative samples in the dataset. Any questions here? Okay, then let us proceed. Now, in general, of course, there can be more than two classes for a classification problem. And some of these approaches actually work the very same way for multi-class problems. Confusion matrix can be created. You just need to increase the number of rows and columns in the matrix. And the success rate and the error rate will be computed in a very similar fashion, the ratio of the correctly and incorrectly predicted classes. Well, but some other measures have to be adapted or extended, such as precision values, because for a multi-class problem, it's not straightforward to define what counts as a positive or as a negative sample. And then you could basically define it by comparing classes against all the others, and you could define average precision for the individual classes and combine them. We will mention this later as well. Okay, so basic predictors, either for binary and multi-class classifications, can be evaluated this way. There's one other direction that I would like to mention, is the case when we have probabilistic estimators. In some models, the output cannot only be the class itself, which is the case for many models, including neural networks or some other ones like Bayesian predictors that are based on the concept of probability. And in these cases, it might not be enough or we can actually do better than just looking at how many of the predictions were correct and how many were incorrect, which we could also define as 0-1 loss function, where loss is basically a metric of how much error did we make. Of course, if you pay attention to differentiate between using it for the success rate or the error rate. Here on the slide, we can see the definition for the success rate. However, if our classifier also is able to give more precise information about its prediction, not only what the output class is, but assigns confidences or probabilities to those classes that are possible, then we can measure the performance a bit more accurately rather than just simply comparing them to the ground truth class. So for example, if our predictor says that the class probability is 100%, then, and it still gets it wrong, then that should count as a more serious error than if it says, okay, I think this class is more probable than the other one, but my confidence assigned to this one or probability assigned to this one is only 51% or 0.51 if we normalize it to a scale from 0 to 1. So if we want to take this into account, then the most typical error measure or evaluation measure to be used is called the cross entropy, which for a single instance can be computed by taking the negative logarithm of the prediction, where of the predicted probability for the given class, which is in the ground truth. And this will basically correspond to the average number of bits needed to identify a random event from a set. And the one specific property of the cross entropy is that it will still reach its minimum if the prediction is correct. But if you are using it for a classification problem where the labels have no probability values assigned, then you have to assume that the positive labels have or the correct labels have 100% probability and the negative labels have a 0% probability. And in this scenario, the minimum is reached at the true probabilities, similarly to the classification, the plain classification scenario. But we still have the advantage that we can differentiate between two models, even if they give the same prediction, just based on how sure they are in their predictions. And if we happen to know cases where the assigned label is can be different for the same input, so we have a probabilistic problem. You can have different true labels for the same input. Then you can basically compute the expected probabilities for a given type for a certain input, and then you could this cross entropy can use for those scenarios as well. Okay, with that we have covered most of the basic things. So I will mention a few things to pay attention when applying these basic evaluation measures. So one is the case if the data set in a binary classification example has very different numbers for one class than the other. So for example, in medical tasks, it's very typical that a disease only occurs with 1% of the test samples, whereas 99 of them are negative. And if you imagine to
Sorry, you are muted probably.
Okay, I hope I can be heard again. I'm not sure who muted me. This has happened earlier too. And please remind me if this happens. Seemingly no technical solution was found to prevent such a
Would
scenario.
you please repeat this one?
Yes, so where should I restart?
From the medical test, you said there's an example.
Okay, so in a medical scenario, in many cases, the tests would include samples, a large portion of which would be negative ones. So these correspond to healthy people, and only a small percentage, say 1%, could be the ones who are affected by the disease, and these would be the positive samples. And if you assume a predictor that is very, very simple and doesn't even consider the input, just tries to guess the output class based on which one is in majority, then you could just go ahead and say negative for all the input samples, and it would result in a success rate of 99%, which we can immediately feel would lead to incorrect conclusions about this model, especially if someone doesn't realize that this is such a simple model and would like to trust it more. This kind of discrepancy doesn't only arise for such simple predictors, but it could happen with way more complex predictors. So we have to pay attention to be able to reflect the true performance of the model, and seemingly the success rate is not able to show us the true nature of the model under unbalanced the circumstance of facing unbalanced classes. So one possible solution, and probably the easiest one, is to go for balanced accuracy scores, where we basically compute recall values for all the classes separately, and we take the average of them. And you could also do this using accuracy, where the samples are weighted according to the inverse prevalence in dataset. For a binary classification, you can just simply take the mean of the two classes. This corresponds to the mean of sensitivity and the specificity. And there is going to be another approach, the so-called ROC curve, which we will discuss a bit later. But as a reference, I wanted to mention it here. This is the abbreviation of the receiver operating characteristic. It's a more advanced type of evaluation measure. So another aspect of evaluation is that we have a task where not all errors would constitute the same amount of problem, because they might not be equally bad. So if you consider examples where you try to diagnose an airplane, then a false positive prediction of an error. So if you find an error in a case when there is no error, causes way less problems than if you don't find an error if there's one. or in a terrorist profiling case, if not terrorists is correct in 99.99% of the time, but missing the single one who is a terrorist, then that could really lead to a really high cost. And we could continue with medical tests or credit card fraud tests or entrance security systems and stuff like that. So these all have very, very unbalanced costs corresponding to the different types of errors. To be able to cope with these, we can define a cost matrix. And pay attention, this is not a confusion matrix. This is a cost matrix, which tells you what is the cost in corresponding to the given cell in the confusion matrix. So the size and the shape is the same for the cost matrix, but the numbers have a very different meaning here. Okay. And if you do take costs into account, then of course, instead of just calculating the number of errors, you would sum up the corresponding cost to the errors committed by the model. And you can use the cost matrix for all types of, so this can be applied to against all kinds of evaluation metrics that we discussed so far. Are there any questions here? Okay, I will proceed then. And one thing we have to mention in terms of evaluation is the limitations of performance predictions, which will stem from, for example, the size of the test set. For example, if we measure a 25% error rate on the test set, it still not guarantees that if we start using this model on newer and newer samples, which we don't have access to at the moment, the error rate is going to be exactly 25%. Of course, because even if those samples come from the same distribution, it will just be a different sample, and different samples can behave differently. There's probability theory and statistics has a large amount of theory about this, which we can nicely use for machine learning. Which I will not go into the details discussing all these. There's a course in the program called the mathematical backgrounds of machine learning. So if you are interested in that, you can hear about these things in more detail in that course. So I just quickly want to mention that if you have, for example, 1,000 trials and 750 are predicted successfully, then this is the same success rate as if you predict 75 correctly out of 100 samples. But in this, the difference in the test set will actually lead to a difference in the certainty about the success rate and the error rate as well. So we can usually say that the estimated rate lies within a certain specified interval called the confidence interval. And each confidence interval has a specified confidence that tells how confident can we be in the actual performance measure falling into the confidence interval itself. So if we have a classic normal distribution, a bell-shaped curve, then we can basically calculate based on the properties of the distribution, what is the chance of the prediction falling inside certain limits. And for a normal distribution, to make our chances to reach 90%, we have to actually increase the confidence interval by 1.65 times the variance of the distribution in both directions. So here you see a normalized data, but of course you can fit the curve onto other data sets as well. But typically what we do is to normalize the data so that it has zero mean and unit variance. So as I mentioned, if you have the chance to pick the test set yourself, then because you are given the data set and it has to, the test itself has to happen on this data set, then you can pick the ones, you can pick the samples that will be contained in the test set. And for that, you typically divide the data set into two pieces, the training set and the test set. And in data science, we refer to this as the holdout method, because as I mentioned earlier, you just basically put the test set samples away and expect the training not to touch them or interfere with those samples in any way. And you have to actually make sure that this is so. So how can we make the most out of our data? Generally, the larger the training data, the better the classifier is going to be. But the returns, as you increase the data set, the size of the data set will be diminishing. There's a very good theory to this. This is a so-called learning theory. The mathematics are not very easy to cover here, but the intuition behind it is not very difficult to grasp. So even if you think about just polls that institutes makes about public opinion, then the more people they ask, the smaller the error they will make. And this is fairly intuitive to everyone, even without a firm mathematical background. So the other thing we have to consider is that the larger the test set, the more accurate the error estimation is going to be, for very similar reasons. Which means that when you split your data set to create the training and a test set, there are arguments for making both of them larger. But this is basically a trade-off between the two, because the larger your training set, the smaller your test set becomes. The rule of thumb here is to use a smaller portion for the test set than for the training data set, which can be 1/3 for the test set or 1/4, 1/5, but something around this ratio is a typical choice. However, once you finish your evaluation and you have your estimation about the performance of the model, you have the ability to train another model using all your data to build the final model to be used. And when you do so, you can have the hope to increase your performance because of the larger data set being used, but still the evaluation that you performed earlier will be unbiased because the model that you evaluated was actually not the one that you return as your final model that has all the data, but only the data samples which were not contained in the test set. So this is probably the best scenario, and your estimation is going to be somewhat conservative then. Another thing to consider is stratification. So if we have unbalanced data sets and the samples therefore are not always representative, then you can modify your data set, which ensure, in a way, which is called stratification, to ensure that each class is represented with approximately equal proportions in both subsets. So both in the training set and the test set. And if you pay attention to stratification, you can avoid the problems caused by rare classes in the unbalanced data set. One of the cornerstone problems in data science is the limited amount of data. The reason for that is that acquiring data or collecting data is costly. And for supervised learning, you need humans or experts to create the labels, which is what we call the process of annotation. And you already saw yesterday that when you create these annotations, more advanced techniques can be used as well than just human labeling, but still the larger the data set, usually the larger the cost. So whatever methods we actually refer to, the problem of limited data is almost always present. So addressing limited sizes of the data sets is very important in data science. We will mention just a few examples to get around this. One of them, which I will explain in more detail, is cross-validation. And there are other possibilities like bootstrapping, where you basically artificially create new samples, and based on the distribution you were provided in the training set. However, you will have to pay the price of creating these new data samples anyhow. So the simplest approach is basically called repeated holdout method. When you create multiple holdout test sets, and this way the random test samples that you take out from your data set will differ in the different experiments, in the different runs. And in these different runs, you always retrain your classifier on the different data training sets, and then perform the evaluation on the corresponding test set. And once you are done with a number of trials, which number you can pick on how much resources you have. You can combine these different error rates by taking their average. And this estimate is going to be better than a standard holdout method. But this is still not optimal because these different test sets will have a large chance to overlap. And a classic method to overcome that is called the k-fold cross-validation. In this scenario, we make sure that the test sets are not overlapping, and we divide the complete data set into k subsets of equal size. And in each so in the k runs that we have, in each of the k runs, we will consider one of these subsets to be the test set and the remaining ones to be the training set. So this is very similar to the repeated holdout method, but with this primary segmentation, we can make sure that there's no overlap between the test sets. And then the estimation of the error happens exactly the same way as previously. Now, because of the visualization, you might think that, okay, but in this case, the test sets are less random than in the previous one, which in this visualization, of course, is something that seems like trivial. And of course, randomization is important. So what data scientists typically do is to shuffle the data set before they launch the k-fold cross-validation. And this will ensure a similar level of randomness to the repeated holdout method, as at least the way it was visualized there. So this is a very standard technique in machine learning. And typically, the most common value for k to be used is 10, but it can also be 5, depending again on your resources. And this is justified by extensive experiments on different tasks and different fields, and typical values. Cross-field results typically show that a 10-fold gives the best performance in terms of average results. And if you use just 5-fold, that can be somewhat less accurate, but it's still very much acceptable. So in the slides, you can see the leave one out cross-validation, which is a special case of cross-validation where the test sets only consist of just a single sample. I'm not going to explain this in detail. It's basically just a special case of the k-fold cross-validation where k is equal to the number of samples in the data set. It's not used very often, but the term itself is something that is good to be familiar with, which is called leave one out cross-validation. And there are certain disadvantages to it too. Stratification is, for example, not possible. And if you have a completely random data set with 2 classes and equal proportions for both, then leave one out cross-validation may return a 100% error rate. Before the break, I would like to conclude with some comments here. So to understand the performance of your model, it's typically good to do a more detailed evaluation, so to have some diagrams. And because the cost matrix is rarely known, at least not exactly. If you can achieve multiple, if you have multiple evaluation metrics in your hands, that will eventually give you more detail about the performance of the model. And if you have ranges for the costs, then you can still try to get the evaluation metrics into a range which could be acceptable even if the costs are different or not exactly known. Are there any questions related to what we discussed so far? Great, then let's do a short break, and I think I will continue in about 5 minutes. So let us continue. So in addition to using evaluation metrics or a set of evaluation metrics, what one can do is to try to tap into the actual performance of the model a bit more. And this will be related to the point where I mentioned probabilistic classifiers, which also return some kind of confidence or probability. Neural networks are one primary example, but there are other models like naive Bayes and logistic regression that also can also return confidence values. The important thing that I would like to highlight here is that in this case, we're not basically using the model. We're not this probabilistic model. We are finalizing it to different output models. So basically, by applying different thresholds on the predicted probabilities to predict a positive class, we can create different output classifiers. So, for example, if you think that you are facing a scenario where false positive predictions might have a larger cost or a larger negative effect, then you can increase the threshold from 50% to 95% and only predict a positive class if the predicted probability is above 95%. And if it's below that, then you will just stick with predicting negative. And this way you can avoid the large costs or a large portion of the large costs associated with false positive classifications. Or you can change it to another threshold level and the third one. And basically, as you move the threshold, you will just get different classifiers. And you can start collecting these classifiers and the results over them, all the evaluation metrics, and try to put them onto a diagram where there is going to be a structure behind them. Now, the tool that is typically used here is called lift charts, which explains, this figure explains it through a promotional mailing example where you are looking for getting the opinion of people, and you might be mailing out 1 million mails and only 0.1% of the recipients would give you a response, and therefore you would get 1,000 responses. But if you are able to identify what is the part of the population where you have higher chances of getting a response from them, then you can decrease the sample size, so the number of mails, to 40% of the original. And because over this population, the actual response ratio is higher, therefore the costs will not be decreased only by 40%. The cost will be decreased by 60% to the 40% of the original cost, but the number of responses will only decrease by 20%. And if you go further and only send out 100,000 mails, then you still might get 400 responses, which amounts to only a 60% reduction in the number of responses. Now, which one is good for you and which one is not is, of course, a question of preference. But at least you have a visualization of your possibilities. And you're not only given one choice, but you have a whole family of choices. Now, if we apply this for machine learning, then we can define a so-called receive operating characteristic curves. And they work in a similar fashion as lift charts do. They were originally used for signal detection to show trade-offs between hit rate and false alarm on a noisy Telegram channel. And then were picked up by statisticians and data scientists, and they have become very, very widespread in data evaluation. The differences to the lift chart that we've seen is that on the horizontal axis, we have the false positive rate, which is 1 minus the specificity. And on the y-axis, we have the sensitivity, which is the true positive rate. And if you plot the models that you get by applying different thresholds to your probabilistic classifier, then this is the type of curve you would expect to see. Now, let's investigate a little bit what the different points on this curve mean. So, for example, if we are somewhere here, okay, let's go with this one. If we are somewhere here, then the false positive rate is actually at 20%, and the true positive rate is at 40%. So seemingly the true positive rate is much higher than the false positive rate. Whereas if you look at the diagonal, this is the line corresponding to the true positive rate and the false positive rate being equal, which can be produced by any random model. So the larger the distance you can observe between the ROC curve and the diagonal, the more the stronger the prediction of your model is. And whether you eventually go with this point with a 20% false positive rate and a 40% true positive rate, or prefer to go up here and have an 80% false positive rate and a 95+% of true positive rate, can be based on your preferences or the costs corresponding. I mean, if you know about the costs corresponding to the different types of errors, then you can take that into account and choose an appropriate point along the ROC curve, which will basically define your threshold. One particular thing that we will mention later is that even with this many possible output models that each correspond to a single probabilistic model, you can have a single number that measures the performance of the complete family of output classifiers. And this will basically try to measure the distance between the curve and this diagonal. But before we get there, let me mention that this is not the only possible curve that we can draw. There's another one which is very famous in machine learning, which is called the precision recall curve, where this is very similarly derived from two basic error measures or evaluation measures, sorry. But whereas the ROC is more related to sensitivity and specificity, in this case, it's the other aspect that we discussed at the beginning of today's lecture is precision and recall. But the precision recall curve is similar to the ROC curve from the point of view that the more it deviates from the diagonal, the better the quality of the classifier is and the performance of the classifier is. So how would a perfect classifier look like? Where would a perfect classifier be? Either as a curve or as a point in this diagram. So a perfect classifier means that the recall rate is 1. We can find all relevant positive samples. And the precision rate is also at 1. So a perfect classifier should have to be positioned up in the top right corner of the precision recall curve space. And if you want to draw a corresponding curve, then this would be basically just a long, long line on the top and reaching this point, and then a vertical line down to along the right side of the precision recall curve diagram. And as I mentioned earlier, the random classifier corresponds to the diagonal. If we look at the ROC curve, now the perfect classifier is very similar, but it is located in the upper left corner in this case. So how can we aggregate a whole curve into a single number? Well, first of all, let's talk about how can we aggregate multiple basic measures. So if you have a specific model which has a certain recall and a certain precision value, you can take the harmonic mean of the two, and that's a well-known, more meta level, so to say, evaluation metric called F measure. And if you have the possibility to use just a single number instead of a whole set of evaluation metrics, then this could be a very good choice to determine how the performance of your model. And this is basically independent of the actual cost and tries to maximize recall and precision at the same time by taking their harmonic mean. And this measure being cost independent doesn't mean that if you know the costs, then you couldn't find a better one. You could actually put in weights where you take into account how much recall and precision should be taken into account depending on your cost matrix. And those are also called F measures, but with this weight parameter, which we typically denote by beta. And this classic one where no weighting is occurred is also called F1 measure, because it corresponds to the special case of beta being equal to 1. Then you can take average precision with different recall rates, and this is called a 3-point average. And another aggregation method would be to take the product of specificity and sensitivity, if you have those, or if your task typically works with these concepts. And getting back to the curves, which I promised to get to, the typical way of measuring the performance of a whole curve is to measure the area under the curve. And this basically corresponds to the probability that a randomly chosen positive instance is ranked above a randomly chosen negative one, which is 0.5 for random classifier and 1.0 for the perfect classifier. Okay. Now, after having discussed a lot of things to evaluate classifiers, I'm also going to shortly discuss evaluating numerical predictions. So in this case, we don't have a finite set of classes, but instead we have a number that the model has to predict. And in this case, similar strategies can be used in terms of using a test set or close validation, and we can do significance tests. But the error measure is something where a novel approach can be very beneficial. So using a binary or 0-1 error doesn't make too much sense, because getting a numeric value exactly, if it's a real number, can have a very, very low probability. If it's a non-integer number, especially if it's irrational, then getting close to the number is actually can have a 0 chance. But this doesn't mean that the predictor is wrong. If we get close enough to the predictor, if the predictor gets close enough to the ground truth value and the difference is small, then we can actually declare that this is a good prediction. And we are looking for an error measure which is able to grasp this difference. Although you can take just the absolute difference of the two values, of the predicted and the actual values, the most typical error measure that is used is called the mean squared error, where instead of taking just the absolute difference, you take the square of the difference. And the reason for this is that it is easier to work with mathematically when you are trying to compute your models. The main advantages lies in the property of these squared sums, that this is a function that we can easily differentiate. So on Wednesday, you saw how machine learning training typically uses slopes by computing the gradient, the differential in the current point, and trying to minimize the error. And we can only do that if we have a differentiable error measure. And mean squared error is typically the most common error measure to be used. You can also take the square root of this, and you can also go with the mean absolute error, where you take just the plain differences, the absolute value of the differences of the samples. And each of these variants can have a relative error variant, where we compare these errors to the mean values of the ground truth. And this can be then the formulae are changed in a way that we divide by the sums of the differences, either the squared or the absolute differences from the mean values for the given data set. Another way, which is independent of the mean and is fairly used, of a fairly oftentimes used statistics, is called the statistical correlation between two values. And this basically tries to look at whether knowing the value of one attribute gives us information about the other attribute in a probabilistic fashion. So if you take the difference between the average and the actual value and multiply it for one and the other attribute, then if this product is positive, then it means that the current sample deviates from the average in the same direction for the two attributes. And if it's negative, then it deviates in the negative direction. And if you compute this for all the samples, then you will see and sum up these products, then if the attributes do not influence one another, so they are independent, then on average, these sums are going to give you 0. However, if there's some correlation between the two, so one has influence on the other or vice versa, then these are going to become significantly larger or smaller than 0. And of course, the scale goes from -1 to +1 because we divide by the number of samples. And therefore, this is a scale-independent measure.
Excuse me, is this the Pearson correlation coefficient?
Sorry, can you please repeat the question?
Is this the R which we are using as the value of the Pearson correlation coefficient?
Yes, you can use it for evaluating your model. Exactly.
Okay.
Okay. Any other questions? Okay, then I will continue. So this basically the formulae here give you an estimation of the correlation that you can compute based on the sample, and give you a further method to assess the performance. And similarly to classification, it's better to use more than one measure. So if you can use multiple performance measures, then it's easier to select the model based on which that you would like to go and use in your live system. And that already brings us to the second part of today's lecture, namely model selection and tuning. So, as I mentioned earlier, please always pay attention to use test sets that have no relationship whatsoever to selecting the model, because otherwise data leakage will compromise your performance. And this is something we will have to pay attention throughout doing model selection, because there might be temptations to use test results when selecting models. So the most basic way to go about model selection is to split your data set into more than just training set and test set, but also use a validation set. And if we split 3 ways, we do a 3-way split over our data set, then we can actually train multiple models and use a validation set to evaluate our models that we are training using the training set. And based on the results of the validation performance, we can pick one model and say that this is the one we expect to perform best. And then to evaluate, to estimate the performance of that chosen model, we will use the test set to compute the evaluation metric or metrics. So the reason to have a separate validation set is to avoid data leakage, as I mentioned earlier. And after assessing the final model on the test set, you gotta pay attention not to tune the model any further. Because once you have a test set result, an evaluation metric based on a test set, your choices may be affected by this result. And then later models will be compromised by data leakage. So the way we typically do this is can be seen on the slide. Do the 3-way split first, and then start repeating a cycle, selecting a model, training the model using a training set. Then we evaluate the model using the validation set, and do this for each and every model. And then we can do the final selection and assessment. This can be nicely visualized with a diagram as well, and it can serve as to help your visual memory to remember that you are going to have way many more training rounds in this scenario, many more models, and you're also going to lose some of your data set from both the test set and the training set. So the kind of trade-off that I mentioned earlier will also apply here. There are many data science competitions where they only provide a training set and a test set. And in order to avoid data leakage, actually, although in this case the samples, the results, the labels of the test set are not published, but when you submit your model into the competition system, it will evaluate your results on the public test set, and you will learn about how well your model does. Typically published on a public leaderboard. And because you know how your model does, you can use this for model selection. So if your model does better on the public test set, then you can go in that direction. And if it does worse, then those changes could be just dropped. And finally, these competitions typically use a separate private test set for the final results. So the public test set could be thought of just as kind of a validation set in these cases. And you can also combine different types of methods like cross-validation, for example, for tuning high-level parameters of the model that we call hyperparameter tuning, and the holdout method for the classic training performance measurement. And the last thing I would like to mention about evaluation in terms of supervised learning is the case of unbalanced classes. Algorithms typically optimize success rate or the mean squared error, but if your classes are unbalanced, pay attention that taking the balanced accuracy could be a much better choice. And for training, instead of changing the evaluation metric, you could oversample the minority classes to basically create a balanced data set from your unbalanced data set. This in theory, this is also possible for the test set to be done, but be careful, because there you might be falling into errors, as when you oversample and undersample the test set, then you just don't know whether those are going to be truly samples that you can trust, basically. So it's better to avoid touching the test set and just go with the balanced accuracy in terms of evaluation. Okay, are there any questions so far? Okay. Then shortly, we are going to discuss evaluating unsupervised methods, only clustering, because this is what we have time for. But the first thing that we observe is that in unsupervised learning, we don't have labels. So in each of the previous evaluation metrics, we made heavy use of the labels that we were provided with. So it's going to become much more difficult to come up with an evaluation metric. There will be two major approaches. One is called the external, where we think that, okay, without the labels, we can't even evaluate an unsupervised method. So some additional data like labels will need to be provided. Or, okay, we'll discuss this later. And the other approach is that we don't rely on additional information, and just really, based on whatever is the output and the input of the clustering algorithm, we try to come up with some measures. So the easier one, of course, is the external one. So let's start with that. And as I mentioned, you either need labels here, or human judgment that is able to tell you which clustering is better, or some kind of a test where you can run the actual clustering and then measure the performance of your system as a whole. Maybe not only the clustering, but if this type of clustering makes your whole system better, then this is probably better. What kind of measures do we have? These typically try to quantify the overlap between the cluster and the external information. This mostly applies to labels, and we can calculate purity, which means how pure the classes are, the ground truth classes are in terms of the cluster assignments, or normalized mutual information, which is an information theoretical metric building on concepts very similar to entropy. And the RAND index and F measure can be computed because, I mean, of course, this is only for in the case of external evaluation, because we do have access to the labels here. The more difficult scenario is when we don't have access to labels. In this case, we what we can measure is that how similar the instances are inside a cluster and how different they are between the clusters. And these are internal evaluation metrics. And of course, you want to maximize similarity inside a class and minimize similarity outside the class, or maximize dissimilarity there. There's an interesting case if we use the same measure for measuring the performance as the one that we used during the clustering. For example, k-means uses distances. So the sum of square distances of the samples from the cluster center, which is basically the intra-cluster similarity. And in this case, the evaluation metric is indirectly computed during the classification itself. Sorry, the clustering itself. Okay, so very shortly about unsupervised evaluation metrics. And today I would like to finish by talking a bit about model elegance or simplicity versus these error measures. So if we have two possible models, which we could call theories, because they could be corresponding to different approaches, which one is very simple and elegant, that explains the data with some mistakes, but fairly well. And another one, which is way more complex, but makes no mistakes on the test set. Then which one do we think is better? Now, this was a problem that arose in history way earlier than machine learning came about. And a famous philosopher named Occam, William of Occam, who lived in the 13th century, proposed the reasoning that if you have the choice between a more complex and a simpler model, but the same performance, then the simpler model should be preferred, because the underlying theory is probably better reflected. I mean, the underlying reasons behind the model are better reflected. It doesn't give you a direction in terms of trade-off between the model complexity or the prediction performance, but serves as a general rule of thumb for making choices. And even if the simpler model is somewhat worse than the perfect, I mean, yes, than the more complex model, which can make perfect predictions, in some scenarios, it can be still preferable. The machine learning principle behind this is called the MDL principle, which stands for minimum description length. And we can define it as the space required to describe a theory or a model, and add the space required to describe the theory's mistakes. And if you describe both of them and add the two numbers and try to minimize this quantity, this will basically guide you to the model that you can expect to perform well on data, on unseen data, basically, unseen samples. And with that, I would like to conclude today's lecture and also the complete course, and just very briefly give you an overview of what we saw today. So we started by the motivation for evaluation, as the primary motivation being the phenomenon of overfitting, and also to have some kind of sense. And we discussed how rest substitution error was not adequate, and not an adequate measure for that. Then we briefly reviewed over the basic performance measures, including success rate, error rate, and the ones that could be derived from the confusion matrix: precision, recall, sensitivity, and specificity. Then we talked about training set and test set, and even three-way splitting to include a validation set. We talked about using a test set in a classical fashion for holdout, and mentioned the possibility of stratification there. And the more advanced variant of cross-validation that requires more computational power or more computational resources, but can give you better performance estimations as well as better final models. And then we talked about numerical predictors and corresponding loss functions. Also, for the classification scenario where these were probabilities, where we mentioned the cross entropy, and we talked about how we can consider costs in terms of making choices, and making sure that our evaluation numbers do correspond to actual preferences. So minimizing the error would correspond to the real life minimum negative impact. And then more advanced graphical or curve-based measures were mentioned, including the ROC and the precision recall curve, and other types of combinations like the F measure and the area under the ROC curve. And final, in terms of using error measures for numerical predictions, we quickly overviewed the mean squared error, the root mean square, mean absolute, and talked about correlation being a possible evaluation metric between the predicted value and the ground truth value. And last but not least, we talked about how we can evaluate unsupervised methods, namely at least clustering methods from the family of unsupervised methods. And we mentioned external and internal approaches. Thank you very much for your attention. And if you have any questions, I will be very glad to answer them. Well, no questions in the chat. I will stick around for a few more minutes if anyone is still reviewing the slides and maybe some questions pop up. And for those of you who are about to leave, I wish you a successful program. And I will still be giving a lecture in the supervised and unsupervised machine learning course. So we might see each other there again. Goodbye. All right. As I see no questions arriving, I will close the session. Please log off myself. And if you happen to bump into any questions, then please contact me via email. Goodbye.